In this presentation, it's my belief that this is an area of discipline that very few have really gone into seriously, and it might be a breeze for some of you guys out there, but possibly not for a few others. Now, this is having to do with a whole nother discipline. Now, the discipline is this. We're used to thinking in terms of applying a voltage to a circuit and then watching what happens. And of course, how much current it draws. And some of you guys were talking about amplifiers and kilowatt and such like that. You're always thinking in terms of how much current is going to draw with the voltage supplied. Okay, now this tonight is a whole different discipline. And this discipline here is having to do with current supply, or when I say current supply, it can be a controllable current. Notice that during this discussion, I will rarely talk about applied voltage. I'm only talking about current that you apply. For instance, who would come up in their right mind and say, okay, put a 12-volt battery across a dead short? Well, the point of it is, somebody says, but I want to measure current through that dead short. Can you do that? And the answer is yes, but to do that, you have to have a power that supplies current. Don't think about voltage, but think about the current. Here we go. We're going to come down here and we'll take our typical tip coming off of Edway, going on over here into our normal area, but here controlling. Now here's the controlling constant current sources is what we're talking about. We're talking about a current which is steady or current that is controllable, but changing the load does not affect the current. Keep that in mind as we apply it to inductors and capacitors. Here we go. Let's do this. First of all, there are keywords that we always keep in mind. That is rate of flow. And they have a container. Well, that would be a capacitor. And we have rate of change of voltage versus the amount of current flow. We may also have rate of change of current versus counter EMF. Reminding you also that 1 amp is a flow of 1 coulomb. Now, normally don't think of coulombs, we only think of amps, but coulombs is going to be important here. Now, first of all, a coulomb, besides being a quantity, well, they tell me at 6.24 times 10 to the 18th electrons. I usually tell students, don't worry about that. It's a bucket full of electrons. It is a quantity, okay? But it's important to keep that in mind. Now, 1 farad as a capacitor, they tell me the definition of 1 farad, it will hold 1 coulomb of electrons at 1 volt. Now, therefore, if you're talking about a microfarad, then of course it will hold 1 microcoulomb at 1 volt. A Henry, there's also a way you can measure a Henry. How do you know if a coil is a 5 Henry coil versus a 15 Henry coil? Well, what you can do is you measure with any instrument, usually an oscilloscope, to measure the counter EMF developed across the coil. And here's the key. A change of 1 ampere per second as a rate of change. We're going to be repeating this business about rate of change multiple times tonight because that is a key factor. There's something else I want to point out. First of all, a constant voltage source requires a low internal resistance. We don't normally think of that, but if you have a power supply that cranks out a really solid 12 volts and you expect it to supply 12 volts, regardless of what current you're drawing in that circuit, in order to do that, you've got to have a very low internal resistance. That is the definition of a voltage source, a good voltage source. Now, if you have a power supply with an amplifier tied into a reference voltage, then that amplifier helps make the low internal resistance extremely low. That's what makes it what it is. However, with a constant current power supply, or let's say constant current source, because I'm going to avoid using the word power supply after this, a constant current source by definition has a high internal resistance and supplies whatever voltage is needed in order to supply this current. So what happens is, as the load changes, the load would affect the current And therefore, this particular source has to adjust whatever is internal to it to supply the amount of current that we need. All right. For this is supplying, well, it may have to adjust the voltage going up and down. We'll talk about that after a while. Now there's some new considerations. This in here is one I have always enjoyed. Capacitors depend on a dielectric between the conductive elements. We don't think of that very often. We usually think, well, capacitor is a capacitor. Well, you know, we now have to think about this tonight. This is going to be a key factor for some of our discussions. Now, this property of the dielectric, guess what? There's a term called permittivity, not to be confused with permeability. Remember, we went over this before, where we had, if you put an iron slug into a coil, because of the high permeability, about 1,000 to 1, it would change, if you will, the magnetic flux with the magnetic effort that was applied. Well, now we're dealing with capacitors, and here we have this thing called permittivity. What's interesting is if you go do some research, you'll have a hard time finding this term, because what they do instead, they have something called the dielectric index. So if you go do some research, which I would like for you to try doing after this discussion here, the dielectric index determines the ability to hold a charge. Now, this charge we're talking about here, instead of magnetic lines of flux, is called electrostatic lines of flux. And the electrostatic lines of flux is the key issue here. Dielectric index is different for glass. It's different for plastic. It's different for paper, even depending on the kind of paper you have. And so there we go from there. All right, now let's go here. Here was one of my favorites. When I was an instructor at Boeing and we were teaching students where well, here's our dielectric. I want you to see something. Here is a brass open cylinder down here, which just happened to be fitting this glass. This drinking glass could go in here with a really nice snug fit. And then we had another cylinder up here that was closed at the top with a metal rod and a ball sitting on top. And this was a nice fit into the glass. So guess what you had? This is now a capacitor. This is one side of the capacitor, one of the conductors. Here is one of the other didn't mean to do that. One of the other conductors up here. And what we would do, now, I don't know if you remember back in the old days when you had a Windhurst machine, that was something you cranked, and you had two glass discs that were very close to each other, and they spun in opposite directions, and you could generate a really good spark. There's also various different size Van de Graaff generators. Those are the ones that had a dome on top. It had a base at the bottom that was metal, and they had a plastic tube that went between them, and they had a belt that would transfer charges from the lower one to the upper one, and you could generate a pretty good spark off of that. Now, what we would do is this. We would sit this down in front of this class, and this is when I was an instructor at Boeing. We would take our Van de Graaff generator, and we'd use some arcing and sparking, and we would charge this thing up. And of course, the sparks coming off of the Van de Graaff generator were sizable, but they were really that big. However, we knew that after a little bit of time, we could take a test lead, a Pomona test lead that had bananas on both ends, and we could put one on the base and one up here on the ball, and we could draw a spark about 1.5 inches long. And when we did that, the snap of that thing was enough to make people kind of jump out of their seats. We did this a few times just to show them that this thing here can really take a charge. Now, if you're familiar with a Leyden jar, this is the same fashion as a Leyden jar. It can hold a really good charge. And by the time they saw this thing here snap, after we charged it and saw it snap, they realized this was nothing to fool around with. So what we would do is we would charge this thing up really good, set the Van de Graaff generator aside, and then we would disassemble this. We'd wrap a test lead around here, and we'd lift this out and set it on the table. Then we would very gingerly reach over here to these guys, which just barely protruded from here. And with one hand behind our back, because we like to dramatize this a little bit, we would very carefully lift this drinking glass out and set it aside. And of course, everybody in class was wondering, what is he doing? Then what we'd do is we'd pick up this brass cylinder and take it over to somebody in the left side of the classroom. Then we would take this cylinder here and take it over to somebody on the right side of the classroom. And of course, when we sit it down on their desk, they kind of like move away from it. They don't know what's in this thing. So then we would say, okay, now pass it around to the back. And the guy that gets both of them in the back, bring them both up. And you should see the scattering in the classroom as they pass this thing around. I mean, this is like when they saw the sparks. This is nothing to trifle with. And then, of course, some smart aleck in the back, he would take this one here and clack it against this one here, and he'd bring both of them up. Then what we would do is we would reassemble this. We would take our drinking glass and put it into this one very carefully. And we'd always exaggerate this, just, you know, drama, a little bit of that drama in here. Then we would take this guy here and very carefully lower it into the drinking glass. Now, what we've really got, folks, is a loaded capacitor, and we proved it by taking our Pomona lead and putting one lead here, and we would take up here. We did not have to touch that. All we had to do is get close to it. And when we got close to it, there was a really good spark, usually over an inch. So what have we done? If you'll notice, here's our capacitor. This is our dielectric. What we've really done is with our copper here, or brass, what we've done is we have deposited on the outside and on the inside of this, we have deposited charges. So negative charges on one side, positive charges on the other. And here's what's interesting. Because of the dielectric properties, these charges are immobile. They don't move around. It needs the conductor to move them around. Now, what I could also do, I could take and I could grab this cylinder when it was out. I could grab it with my hand and not get bit. But it would be very, very foolish for somebody to do that and then thrust their hand down inside there. You only do this once, then we call 911. It would seriously bite you. So we had to be careful not to let students do something foolish. You know, some of them had to say, well, I don't believe it. I have to see it for myself. And I said, hey, be very, very careful, because if you grab a hold of this on too large an area, they may be immobile from here to here, but when you've got your hand wrapped around it, you are picking up a whole lot of possible charges. And when you stick your hand inside here, you will get seriously bit. Okay, here's what I'm getting at. The charges can be, if you were to take this out and suspend this in here, the dielectric would be air. Could you charge it? And the answer is yes, to some degree, because even the air would be a dielectric. However, if that air moves around, your dielectric is changing on you. Do you see what I'm getting at? If you were to put sheet of paper in here, you'd find that is, instead of this guy here, you'd find that your dielectric would still be good, but not as good as this plastic drinking glass. If you were to put a glass in there, you also have the characteristics there. So here's what I'm getting at. I'm really emphasizing the dielectric is where the charge is maintained, and those charges are immobile on the surface of the dielectric. It takes this conductive material to make them pass from one to another. All right. Now, I assume you have no questions here, so we'll go back. We always had a lot of fun with that, because what we do is we'd say, okay, is everyone convinced that the dielectric is where the charge was kept? No one ever forgot this. At any class that we've had to go through this, it was one of those demonstrations that no one ever forgot. Okay, the permittivity of your dielectric is called the Dielectric Index, and that's where you can find tables of this if you do research. All right, now let's go on from here. This is where things get a little bit interesting. as we go down this, we're going to discover where a constant voltage causes a rate change and a rate change causes a constant voltage. And you say, well, that sounds like a lot of double talk. All right, we're going to get to an area where it's not double talk at all. Okay, we remember this. Capacitors react to voltage changes by drawing a discharging current. Well, this is the way we normally think of it. We're going to depart from this tonight into a whole different mentality. We also know that inductors react to changes in current by opposing those voltages or by producing voltages, because after all, there's a voltage to voltage aspect here. But what happens in a capacitor if we deliberately control the current fed to a capacitor? And what happens to the counter EMF of an inductor if we don't change the current? These are questions that we will be looking at very shortly. In that same respect, what happens or what determines the counter EMF of an inductor if we increase or decrease, keyword, rate of change. Rate of change of what? Rate of change of the current. We got to emphasize current. So from now on, all the way through the rest of our discussion, we're going to talk about current and the control of that current. Now imagine, if you will, well, to begin with, if you had a container for compressed air and with a pump supplying a flow of air at a consistent rate, we can determine what the pressure would be as we build it up. So if we have a flow of air, just consistent, then and if we had a pressure gauge, we could see the pressure gauge climb at a steady rate. And in that same respect, we can also dump that, shall we say, air tank. Now come on down here. Now, here we go. Let's take, this is where we really get serious. And by the way, this is where you have to have a whole different mental discipline than what you normally think of with feeding capacitors and coils with voltage. Here, we are using a current, and the current is held to a particular value for a particular period of time. That's this. If we take this capacitor and feed it with a constant current, it will charge at a linear rate of change. Notice here's what we got. There is a constant current will cause a rate of change of the voltage of the capacitor. Let's do an illustration. We can go back through this, but I want to do it this way. Take a look at this drawing. Now, as before, when you have a capacitor that is, shall we say, totally discharged, if you try to apply a voltage to it, we said that that capacitor is a dead short. Well, you know what? If we are controlling current, that's no problem. We can feed 10 mils into a dead short. We can feed 10 amps into a dead short if we have the right electronics. Here, what we're doing is we are deliberately not even thinking about voltage. We are deliberately taking a 10 mil source and feeding it into the capacitor from this time here, from the get-go to this time here. During this time, this capacitor will charge at a linear rate. Now, I'm not putting a particular voltage down here, although it is mathematically obtainable. It is charging, and notice here, it is a linear charge. Up here, if I have a steady current, however I do this is not the moment, not the concern at the moment, but we are going to maintain an absolute 10 milliamps during this time frame. And when we do, it will cause a rate. And I want you to pay attention to the slope. Slope is a key issue here. And we're going to be talking about slopes again in different areas. Notice now, if we suddenly jump it up to 20 milliamps, now it's still going to be constant, but it is a controlled constant. So now it's up to 20 milliamps. We hold 20 milliamps for a definite period of time, unchanged. It will not waver from that. It's 20 milliamps. What it will do is now the capacitor will start charging at a faster rate. Notice the slope is a higher slope. And that's because it is 20 milliamps, twice as much as this 10 milliamps. And so therefore the rate of charge, the rate of charge is steeper because it's 20 milliamps. Are you with me so far? Now, if I drop down to 15 milliamps, that's halfway between 10 and 20, we are still charging the capacitor. However, our rate of charge is less than it was at 10. And I'm sorry, more than it was at 10, but less than 20. Then, as we drop from 15 down to 5 milliamps, we are still doing, during this entire time frame, we're still charging the capacitor, but the slope has changed dramatically. Now, this is not really all directly to scale. This is just kind of a draw out on a hypothetical basis. But understand that these are mathematically determinate values that you can do on this. When I drop my 5 milliamps of charge down to 0, it will stop charging. And at that point, from here on, the capacitor will have a sustained voltage. So what I'm doing is I come in with these controlled currents. These controlled currents, every one of these are charging the capacitor. But the question is, what is the rate of charge? And it depends, of course, on the size of the capacitor. Obviously, a small capacitor will charge more quickly. So there is a rate of charge, and it is based on a slope. You can see the slope here. If you were watching this capacitor with an oscilloscope, you would see it start to climb accordingly. Now, you wouldn't see this on the oscilloscope, but you would see the voltage rising at this particular rate. Now, notice what I've done. The only voltage we're looking at is the voltage on the capacitor, which is a result of, guess what? Accumulation of electrons on one side and peeling them off on the other side, because that's what represents the differential of the charge across the capacitor. So the only voltage applied that we're looking at here is the voltage of the capacitor itself, but our circuit up in here, and this is where the mental discipline comes in, up in here, our mind has to be, what does current do to this circuit? And as long as this current is constant, the rate will be linear. That's an important point. The rate will be linear. So as I go to more current, I have a steeper slope. Less current, I have less slope, but it is still consistent. It is linear. As long as this is straight line, this is linear. Are you with me here? It almost makes sense. But like I said, this is a mind bender for some people because they're so used to thinking in terms of, what about the voltage? Well, the voltage is here. Now, I will grant you this. It may be possible that to maintain 10 milliamps here, as the voltage here rises, these two voltages will be in contrast to each other. Therefore, this circuit over here is making adjustments, but that's what makes it a current source. It will make whatever adjustments it needs to in order to maintain 10 milliamps constant. Come on. All right, questions? Any questions? Okay, now that's for capacitors. Going back here, what we're finding is that, note particularly that the rate of change, which is the rate of charge, will be altered to be less, that is lower slope or higher slope, depending on what? The actual value of current. Remember, we're emphasizing that we're driving current into this circuit. Now, normally, like I said, we normally think of voltage. We apply a voltage and watch what happens. Well, here we have a special situation where we have a current source that is controllable. I'm leaving out some of the details of all that, but nonetheless. All right, final note. With the capacitor, the rate of charge or capacitor voltage occurs during the value of the charging current. So this is our emphasis, is on current supply. Okay, now let's go into another one here. Now we're going to do this one, and feeding an inductor with a constant current. Well, that's kind of an interesting situation. If you feed an inductor with a constant current, what's the EMF? Anybody? Zero. There is no EMF. If you have a particular current and you've either built up or fallen down to that value, and now the current is constant, there is no counter EMF. However, what happens if you suddenly change that current, or what happens if you suddenly drop it out altogether? If you drop the current out very suddenly, there's an engineering formula that says that the voltage that will be produced is equal to the change in flux versus the change in time. And if that time is very, very short, you can take what is normally a 5 or 6 volt circuit and you can develop a couple thousand volts. The formula is called E equals d phi dt. I thought about putting that in here with the Greek symbols, but I decided, okay. All right. As the inductor is not a storage unit, well, wait a minute. It's not a storage like a capacitor. You can charge a capacitor and set it aside for some unsuspecting pole to pick it up and test the terminals. And of course, anybody that's ever been in this field for a long time has done that one time or another. And you have to be careful because sometimes they throw it across the room in their reaction. However, if the current is established and say it's constant, there is no counter EMF. But as the inductor is not a storage unit, that is, it's not keeping a charge, there is no collective value except for the energy stored in the magnetic field. Okay, now let's go on down. If you take and feed an inductor with an increasing current rate of change, okay, we have here, if the current is increased at a linear rate. Notice my emphasis. I did this on purpose. What do you expect will happen? If you have a current increased at a linear rate, here's what fools most people. You can usually, most of them do a double take on this. The counter EMF will be a constant value. And you say, what? Depending on the inductive value. Well, let's take a look here. Look at this drawing. Here we go. Since pictures are worth 1,000 words, let's do it this way. Here's current starting at 0, and it's rising up to 20 milliamps. Now, I want to point out something. The 20 milliamps is not what's important. It's not this value. It is the rate of change from 0 to 20 in this time frame. As it goes from 0 to 20, the inductor will have a consistent voltage opposing that, a CEMF opposing this rate. It's a linear rate, but here the inductor is going to put out a solid voltage throughout this entire time frame. So the point is, and this is what really fools people, I mean, you'd expect it with a capacitor, but look here, that says that this guy here is flat right across here. If you had an oscilloscope on that inductor, you would see a voltage that goes straight across the line. It will not change during this time frame. So as long as this is linear slope, it's not the value that peaks at. That's not what's important. It is the rate of change. As long as there is a linear rate of change, the inductor will have a consistent flat line value right there. Now, here we drop from 20 mils back down to 0, but notice it takes longer than it did to go up there. Therefore, the rate of change is less than over here. In fact, the rate of change is about half of what it was over here. And when that happens, the inductor, the counter EMF, will be backwards. It'll be assisting the current flow as the magnetic field collapses. So as the magnetic field collapses here, the inductor will produce a voltage in the opposite direction, in the direction to assist current flow. The inductor will try to make this current keep going. And so therefore it produces an opposite voltage. And if I had scaled this right, it maybe be just a tad less right in there. Do you see that? So this is not really necessarily to scale, but it is to illustrate a point. Now here's something else. Here I'm only going up. Instead of going up to 20 milliamps, I'm going up to 10 milliamps, but notice that the time frame is a lot less. And since the time frame is a lot less, the rate of change will produce a greater voltage, counter EMF, across the coil. And this counter EMF across the coil, you can actually observe this with an oscilloscope. And in fact, this is a method that you can use to determine how many henries that coil is. You can mathematically determine that because a rate of change with a coil is that a rate of 1 amp per second across 1 Henry or through 1 Henry will produce 1 volt of counter EMF. That's a rule. Therefore, if you have a 5 Henry coil, a 1 amp change in 1 second will produce 5 volts counter EMF. So that's what this is. This is a rate of change, even though I'm only dealing with milliamps. By the way, if I was to go from 0 to 20 milliamps and from here to right here, I wouldn't have this little bit of voltage. I would have a lot of voltage. You can generate hundreds of volts or even thousands of volts if your rate of change is fast enough. So now here we go. Here we up here at 10. And this time the slope here is even longer or a lesser slope than what it was here. And guess what? The voltage from this in time frame from here to here, as long as this is linear, it will travel at, I should say, it will produce a counter EMF less than it did over here. Now, if I hold at 4 milliamps, hold it steady all the way out, no counter EMF. I happen to know from experience that this drawing here is one people have to chew on for a while before they finally, get it all together here. Did I lose anyone?
No, it's super interesting, Dave. But there is one thing you brought up that's back on the capacitor.
Okay, I'll go back
illustration. It's not really a question, so maybe it's a question. I don't know, but
all right, that's right here. Illustration of
what? You could even I was under the understanding that the electrons built up on the plate, on one plate,
and then removed on the other.
And were removed on the other, not the dielectric.
Well, actually, the plate contributes to the dielectric. It conducts these charges to the dielectric. That's why the dielectric index determines how much you can transfer to the dielectric.
It gives up the electrons.
Yes. So what happens is the dielectric index determines how much you can transfer to that dielectric.
Okay. I was just about to blame my old instructors, but you know what? That's coming back to me now.
All right. Now, okay. Now I'm going to go into something that's not on the chart, but I'm going to throw it in here. Let's say, okay, go ahead, Barry.
I hope it's not a trick question. So suppose your dielectric is air and you have just 2 big plates separated by some distance with air and you build up a charge on it.
Yeah, they would be primarily only on the plate.
Yeah. And then you blow away the air.
That's right. So therefore, air does not retain it very well. That's why it has an index of 1. But here's something else though. But here's what you can do, Barry. You can actually charge the air to ions.
Yeah, never mind that. If you have 100 volts in there and you blow away the air, trust me, you still have a 100-volt charge.
But it's primarily on the plates only. The dielectric because the dielectric index is so low, it will not retain the charge except for ionization on the air.
Okay, so if you blow away the air, then is the new air get the transfer of the excess charge?
It can, yes. Yeah.
I thought I understood it. Now I don't think I do.
Well, here's okay.
Never mind. It's a trick question.
Yeah, well, that's a question I have surmised myself, by the way, a lot of times. Let me throw something else at you. We know that the capacitance is determined by the square area of the plates, right? And we also know that the distance is a square law relationship. In other words, the closer the plates are, the greater the charge can be. because of how they affect one another. Would we agree with that? All right. Let's say that somebody comes up with an ingenious method of making these two plates a micro-inch apart. Would you say that that could substantially raise the capacitance, except you have a very low voltage tolerance before you have arc over?
Sounds like electrolytic capacitors.
As a matter of fact, that's where we're heading. Now, how do we do that? Did you know that when electrolytic capacitors of this nature are first made, they are not a capacitor? They're actually a resistor. What happens is you take let's say two aluminum foil, and you wrap them around each other, but you have a liquid electrolyte inside between these capacitive coils, or I should say metallic surfaces. Then what you do is that is a conductive material. And a lot of people don't know this, but it's a conductive material, and those capacitors are not formed yet. Here's what I mean by forming. In the factory, what they do is they pass a gradual electric current through them, but I apply a voltage to make the current go. So now we're talking about voltage, current, both. As the current flows, it ionizes this material, but it also causes a deposit on one of the aluminum surfaces. And that deposit, which comes out of this electrolyte, causes that particular surface of the aluminum to become non-conductive, an insulator, but the other surface is still conductive. And so now what you have created is two plates that are close to each other, but the liquid makes the distance close in, and the insulated material that's formed on the one capacitor is your dielectric. And what you've done is you have electrically created two plates that are extremely close to each other, and hopefully not too close to have a problem with voltage breakdown between them. That is now.
It turns out that capacitor forming is important, and I have a big storage of several kilojoules of capacitors back here, and after they're not being used for a while, I do exactly that routine to refill.
Okay. All right. In the early days of the S100 system, that's a true story. We were building systems by buying cabinets from one manufacturer, power supplies from another manufacturer, and putting them all together into making a complete S100 system. And then we would program it in-house, and then we would custom program these for different businesses. And that's actually what we did with law enforcement. Well, when I put one of them together and I fired up an 8-inch floppy, which is what was in business at that time, the 5-inch had not come out yet. And this thing would not work right. And I went, what is going on? And I got this sneaky suspicion that I had way too much ripple in the power supply. So I put a scope on it, come to find out, brand new capacitors in that disk drive unit had never been formed from the factory. I was rather upset. But I knew what was to be done. So I did what you're talking about. I took the time to hook up a very slow process to build these things up until finally they're up to what they should have been, and then everything worked fine. But had I not known about the forming process, I wouldn't have known what to do. There you go. All right, other questions? That air business is rather interesting. By the way, a true one is a vacuum. Now, what do you do in a vacuum? What's the dielectric? There isn't any. It is the plates only. So that's a true one. I don't know what the formula is for air, but they also claim it has to do with the density of air, the moisture in the air, and you get about 1.000 something or other. Walt, do you remember anything about that? You're muted. Walt, there you go. Okay.
That's correct. And I would say that in the absence of air, or when you blow the air, the electrons and the holes, if you please,
The ions, yeah.
are attached to the plate by the charge. So they don't move with the air that Barry is blowing through.
Otherwise, unless you force them through, then you have some ionized air. Well, anyhow,
Hey,
the
Dave,
point, yes, go ahead.
this is Frank. Okay, those capacitors that I remember way back when somebody had said, oh, the capacitor has lost its form, and not knowing what the heck he was talking about and everything else. I thought, oh, okay, it was in a millivolt battery generator, that we used for a lot of instrumentation, chromium, alumel stuff. Anyway, and so I just took it for granted that it broke. You said that it lost its form or didn't have the form, and everything. How did you form it?
First of all, what I did is I put a variac on it to bring the voltage up very slowly so that I could allow time for them to charge. And actually, I did this over a period of several days.
So if it was like a 50-volt electrolytic, you'd put a variac on there and slowly bring it up with a DC power supply, slowly bring it up to.
Well, actually, I used the transformer and rectifier filters, the rectifier system. So I had pulsating DC. So I just had made sure that I had less voltage because I did not want them to come up too fast.
Yeah.
And by the way, if you hook up a capacitor backwards, it's not a capacitor, it's a bomb.
Kaboom. Yeah.
It's a bomb.
Yeah, we've done a few of that, plug it into AC.
Yeah. One of the other things that can happen is if the paste that's between the two elements becomes aged, if you will, then the dielectric property of that can actually affect the capacitor and diminish its value.
Okay.
So, well, anyhow, I really hope that by going this route, by taking away from the normal voltage aspect and concentrate on controlled current maintained at a constant value, and look what it does. And you can do this with certain circuitry. As an example, in transistors, and we did this with tubes also, a grounded grid amplifier had the characteristic of maintaining a constant current. A common base configuration for a transistor has a very interesting characteristic. It's a constant current source. It works excellent. And you can change the load over a considerable range and it will deliver whatever current you tell it to deliver, up to limitations, up to limit. All right. Now, let's do this. Let's go on down here and see if you followed me through all of this. All right. If we've done this on the inductor with a constant rate of change, how about right here, gentlemen? Let's do this. Now, I want you to concentrate on this drawing right here and this drawing right here, what we have. Let me move this around a little bit. There's one error in that circuit. There's one error in that circuit. I saved this as so I could say there's a test following.
Could it be that? Sorry, Dave. Could it be that final 5 milliamp stretch towards the right? It looks like the rate of change is too high, isn't it?
That is correct.
Is that my
No,
eyes?
you're right. Absolutely right. That's it. I made this drawing just on purpose so that we could see if you really got this. Yeah, that rate of change for 5 mils is totally wrong. It should be very shallow.
Flatten out, yeah.
Because 5 mils is, yeah. All right. That looked pretty good. All right. Now here's another one. Okay. There is an error in this one. This is a coil. And we're shoving current through a coil. So what we do here is we start off, we go from this current up here and down here and up here and down here. And then finally we go across and sustained. What's wrong with this drawing? Notice the rate of time. This is the time segment, drops down here. I just didn't put anything in here to indicate time markers. But as we are raising, we cause what? This is a rate of change. And we have a constant voltage. Then we have a rate of change that's not as much, but in the opposite direction, so it goes negative. Then suddenly we have a rate of change from here to here, and guess what? We have more voltage. Wait a minute. See this guy?
That should not have caused that much negative voltage.
Exactly. It belongs right about in here. Hey, very good. You all passed the test. Go to the head of the class, right?
Dave, I got a quick question for you.
Fire away.
When you see capacitors like in a garage door that blow apart, what is it that's breaking down? Is it a dielectric?
Yes.
Capacitors go bad. Is that what goes to pieces?
Yes. Unless it's something like a drinking glass made out of plastic or glass, either one, not the same thing. You know, the plastic mailing envelopes, a lot of times in a company, they'll have a plastic mailing envelope for one department to another, sending stuff. We would take one of those, and what we did is we put an aluminum plate inside, and then we took two plates on the outside and connected them together. That was our Leyden jar, and we charged that thing up, and we got it up so high that when you got enough voltage across it, there was voltage breakdowns, and it would burn holes through the plastic.
Jeez.
And they were visible. I mean, you could hear them snap through. You wonder, whoa, what's going on? If you put paper in there instead of plastic, it really makes a difference what kind of paper you have, because paper is really quite fibrous if you look at it under a microscope. So yes, you're right. That's what makes them blow up. That's why they blow up if you happen to reverse charge them, is because it is no longer a capacitor. It is a resistor with liquid, and that liquid overheats, and away it goes.
Let me add just a little bit more to that.
Sure.
The failure mode for electrolytic capacitors that you might see on a motherboard is most often the case, is that the capacitor internally suffers some leakage. There's some pinpoint or multiple pinpoints where it's a resistor for a tiny area on the aluminum, and the current flowing through there will heat up the inside of the capacitor, I squared R,
Yep.
and eventually boil that electrolyte, and it expands. And
Yep.
that capacitor is built without a pressure release mechanism of some sort.
Yep.
It'll put up a lot of pressure and literally explode.
Oh yeah, I've seen it
Modern
happen.
capacitors have some scoring on the top, which is a weak point. If they build up pressure, they'll gradually expand and burst through the top.
In the class one time, this was beginning to happen. I could see the capacitor swelling, and I reached over and flipped the switch off because the student didn't realize how close he was to having that bomb blow up. So now here's something else for you. Now this has nothing to do with this kind of a capacitor, but would you agree that a car battery is in fact a capacitor? And in fact, if you have too much current going through that car battery for any reason, for an extended period of time, it can bellow out the sides and blow up the battery. I actually had a car battery blow up in my face one time. One of my students was showing a bunch of us his car, his new car. That is, it wasn't brand new, but it was new to him. And he had the hood open, and all the class was over on one side of the car, and I was on the other side. And I happened to look down, and lo and behold, the battery cable was rubbing against the frame, the hot cable. It was arcing and sparking. And I was going to move it, and I hollered, "Hey, we have a problem here." And right at that instant, the battery already was too hot, and it blew its innards out. And I was above it when it happened. Fortunately, I had glasses on. I had little hot spots in my beard. I had to go, shall we say, wash a little bit.
How about, tell them about the bomb that can occur in inductors, particularly electric motors.
Well, if a electric motor is, shall we say, stalled, all of a sudden you do not have counter EMF, and as a result, you now have full current that is not backed. In other words, when the motor is spinning, the current that's there is changing, and as it changes, it produces a counter EMF, which keeps the current, shall we say, sheltered down. And if you stall the motor, all of a sudden there is no counter EMF, and the current jumps up to about 3 to 4 or 5 times what it should be, and the windings go smoke. Is that what you're talking about?
Oh, I was thinking about the field windings on motors, which which carry a lot of current in it, but that's okay because it's just circulating in there. And then if some student in the lab, for example, pulls the wire from the field winding,
Oh,
then the magnetic field collapses, and oh, guess what? It will generate absolutely any voltage necessary to keep that current going, which can be
yeah.
thousands of volts. You can
Oh,
draw
yeah.
a huge spark when you pull the
Arc
field.
and it's, yeah.
So
By
is
the
that
way,
two-
by the way, the 5-inch guns on a ship are controlled by an amplidyne, which is a motor generator combination. And what you've got, because I was the guy that tuned those amplifiers, what you've got is feedback that comes in and directional control. And what happens is this amplifier feeds the field with the proper amount of shall we say, excitement. And as a result, then the excitement in the armature is carried to the motors on the gun mount. And depending on what you do, that gun mount can move so fast that, like when I was doing changes on these, there's a place in the gun tub marked dead man. And there's a few places that are marked dead man, which means if you are there when that thing turns, you do not have time to jump, twitch, or anything else, and you are a dead man. So I had to be extremely careful when I was making adjustments. I had to have men on various different stations. I had to make sure that the guy on the gun was hanging on, because if I did something wrong, hit the wrong terminal, that amplifier, the amplidyne combination could really make that thing go. And so I had to be on top of my game all the time. Well, that's all I have, gentlemen.